Hey guys, welcome back. This is the third video about vectors. We're still looking at vectors in the plane. We're going to talk about finding component form of a vector given the length of the vector and the angle that that vector makes with the positive x-axis. We'll talk about standard unit vectors and how they will allow us to write v with a new notation. And we're going to talk about the components of v. Now that can be a little ambiguous. Sometimes we're talking about scalar components, and sometimes we're talking about vector components. And I'll show you what I mean. So let's say you're given the length of v, and the angle theta, where theta is the angle that v makes with the positive x-axis. That same angle from trig. So it looks like this. Let's just make theta acute. Might as well. All right. The question becomes, what is the component form of v? Well, we can derive it geometrically just using what we know about right triangle trig. We can also think of this as rescaling a vector that's on the unit circle. So we're going to look at it both ways. First, let's derive it using right triangle trig. Now we already know that the x component of v is this length, and the y component of v is this length. So I can draw a right triangle, one side parallel to the x-axis and another side parallel to the y-axis. Well, you know from trig, if that's theta, this is the side that is next to theta, but it's not the hypotenuse. That's called the adjacent side of the triangle. And this side of this triangle is opposite theta. It's directly across from theta, so we say it's opposite theta. So I might ask myself, if I know the length of v and I know theta, what do the adjacent side and opposite sides have to be? It's pretty simple. The length of v, that's known, and that's the hypotenuse. If I know this and I know this and I want the adjacent side, or I know this and I know this and I want the opposite side, I can use sine and cosine. Remember back from trig, you learned SOHCAHTOA. Probably been a little while, it's okay. SOHCAHTOA reminds us that sine is opposite over hypotenuse. So sine of theta is the opposite side over the hypotenuse, the ratio of those two sides of the triangle. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. We don't have both of those, so we're not going to use that. We're going to use these two. Now, it's assumed that we know theta. If I know theta is 45 degrees, I know sine of 45 is square root of 2 over 2. That's just a number, as far as we're concerned. And the hypotenuse is known. I'm trying to find the opposite side. If this is known and this is known, all I have to do is multiply by the hypotenuse to get the opposite side by itself. So the opposite side is the hypotenuse, the length of the hypotenuse times the side of sine of theta. Or in our case, the length of the hypotenuse is the length of v times the sine of theta. And the adjacent side, I know this and I know this, that's going to be the hypotenuse times cosine of theta. The adjacent side is the x component. So v is the magnitude of v times cosine of theta. That's my x component. And v's y component is the magnitude of v times sine of theta. Just using some right triangle trig. That's one way of doing it. Now you can think about the same idea, slightly different way. Probably been a little while since trig class, that's cool. do a little review. This is not looking like a unit circle. It's supposed to. Looking like something else. That's a -1. That's a 1. -1, 1. -1, 1. And let's say this is our angle theta. Remember from trig that the x value on the unit circle is given by cosine of theta, and the y value is given by sine of theta. If that's true, then this vector from here to here, let's call that the vector u. Well, actually, I'm going to put a hat on it because it's a unit vector. It's on the unit circle, so that radius is 1. So the length of this vector is 1. Cosine of theta is my x component, sine of theta is my y component. And I know that because that's the x, that's the xy pair at the end of that point, and we started at 0, 0. So whatever those two numbers are, if that's negative square root of 2 and or negative square root of 2 over 2 and positive square root of 2 over 2. Those are just the components of my u. Those are just a couple of numbers. If I square them and add them, take the square root, I'm going to get 1 because I'm on the unit circle. Now the question becomes, okay, if I take this vector that's 1 unit long and I multiply it by 5, well, it's going to give me a new vector. It's going to point in exactly the same direction. It's just going to be 5 units long. So the vector v, which points in that direction but is 5 units long, well, first I take the unit vector, cosine theta, sine theta, and I multiply it by the length. And remember, we know how to multiply with scalars, so we just multiply the scalar through. Each component gets multiplied by the scalar. And we get the same result that we had up here. So if you know theta, the angle that your vector makes with the positive x-axis, and this has to be 2D, then v is its length times cosine of theta, that's its x component, and its length times sine of theta, that's its y component. All right, so we've been doing all of this for a while. We have not talked about standard unit vectors. Remember, a unit vector is 1 unit long. If I am in 2D, I'm in the xy plane. Let's say I'm looking at the vector x equals, or at the vector with components 3, 4. Maybe this is my vector v, just for example. I can write that way. Go 3 units in the x direction, 4 units in the y direction to get to the terminal point of v. I can also write it in terms of what are called the 2 standard unit vectors. Since I'm in 2D, I get 2 standard unit vectors, one that goes in the x direction and the other one that goes in the y direction. They're always perpendicular from each other because our axes are always perpendicular from each other. This unit vector in the x direction, it's called I hat. You go 1 unit in the x direction and 0 units in the y direction. And the unit vector in the y direction is called j hat. You go 0 units in the x direction and 1 unit in the y direction. Now watch this. This can be split up. I've written it as 3, 4 like this in component form, but I could also write it this way. Isn't that the same as this? Remember how we add vectors? We add component by component. Is 3 plus 0 3? Yes. Is 0 plus 4 4? Okay. So now I've split it into 2 pieces. This is the piece in the x direction and that's the piece in the y direction. Now I can even go further. I can factor out that 3 and factor out that 4. Well, that's just the definition of I hat, and that's just the definition of j hat. So I could write my vector this way as well. So here's our alternate notation for v. We can write it in component form as 3, 4, like this. I prefer this form because it's really easy, it's nice and fast, but this means exactly the same thing. We have 3 times I hat, and then you're adding 4 times j hat. And because of all of this, because we've proven it algebraically using all of our properties of adding vectors and scalar multiplication, these two guys are equal. I can write it either this way or this way. This says go 3 units in the x direction, and then 4 units in the y direction. Now, another way to think about this is to think about this geometrically and say, well, what is this vector? Well, I hat is right here. If I take I hat and I multiply it by 3, I get 3 I hat, which is that vector. I start at the origin and I go out to 3. Well, this says, if I'm adding tip to tail, start at the origin and go out to 3, and then start where you start where you end up right here, and then go 4 units in the y direction. J hat is just one of these, so I'm going to go up 4. So this is 3 I hat, and this is 4 j hat. And when I add them tip to tail, 3 I hat plus 4 j hat, start where you started, end up where you ended up, I get the vector v. So whether you're proving it algebraically or actually computing that sum geometrically, you see you're getting the same thing. If I go from here to here and then here to here, it's the same as going from there to there. Now this is going to be very convenient. I often want to split my vectors into components that go in certain directions. Like this is the part of v that goes in the x direction. That's the part of v that goes in the y direction. And if I add those two guys together, I get v in general. It's going to be very helpful in this class as well as physics. All right. I guess the last thing to talk about is scalar components versus vector components of v. So I'd written v a couple of different ways in that last example. I had 3, 4 like this in component form. I have it written this way. This is called writing v as a linear combination of I hat and j hat. Or in other words, it's saying, hey, take I hat and j hat, multiply those two guys by constants, add them together, and then we're going to get this other vector, v. So we're saying that v is a combination of that, just multiply by constants and add. That's what linear combination means. Now when somebody talks about the components of v, this is now an ambiguous word. So be careful. They could mean one of two things. If v has these components, the x component of v, which we normally call v1, that's 3. And the y component of v, which we call v2, that's 4. Like these are the scalar components of v. Sometimes when they talk about the components of v, they're asking for the scalars. Now sometimes when they're talking about the components of v, they're not asking for the scalars. They want the vectors. They want 3 times I hat and 4 times j hat. That's what they're looking for. These are called the vector components of v. Whenever it's ambiguous in our class, I'll tell you which one I'm looking for. But just be aware as you're reading different books and other resources out there, sometimes they're talking about this when they say components, and sometimes they're talking about this. And they might even be talking about entirely different components. What if I didn't want the component of v in the x direction and y direction, but I wanted the component of v in this direction, in some perpendicular direction? I wanted to add those two guys together to get v. Well, that's possible too. So just be aware that components could be referring to scalar components or vector components.